Hi, we are now in Module 4. So to start with, in the next 2 weeks, you will be able to demonstrate understanding of the properties of molecular covalent bond compounds in relation to their structures. And now I will give you a summary or a run through of this module and some clarifications for the Let's Prepare. So in this module, you will encounter geometry of simple compounds, polarity of simple molecules, and its application in everyday life. As I was saying earlier, let's prepare. I have some clarifications because of the terminology. So instead of fidget ball, it should be a Haberman sphere or an expanding ball. It will be of the same output but a different product. So design an experiment for a Haberman sphere or expanding ball. The things you need to prepare here are your design is the problem, state the purpose of your creating a Haberman sphere or expanding ball in relation to molecular geometry and polarity. What does this mean? So questions like why are you creating a Haberman sphere aside from it as a requirement in relation to geometric shapes? What is its possible relation to our lesson or to the geometric shape? And then materials, you list down all the materials you will be needing and then explain why you choose such material. The step-by-step process should be included in the design. And then conclusion is the explanation of creating the Haberman sphere or expanding ball. Questions like, were you able to achieve your goal? Relate the study of geometry to creation of Haberman sphere or expanding ball. Questions like that should be in the conclusion. And instead of the Haberman sphere being functional, it should be feasible or can be functional. And together with it is the rubrics. So please do read the rubrics for you to be able to achieve the highest possible score, which is 30 points. Next is the exercises, which is a review of the Lewis dot structure. And then for the first reading, so these are the important points. Lewis dot structure is just a step of determining how molecules interact and bond. Knowing its possible geometry may answer as to why a molecule is in a certain state and how it will combine with other molecules or disintegrate with it. The valence shell electron repulsion theory will give shape to our molecules. It predicts the distribution of electron group, and you have two terminologies to consider. These are the electron group geometry and the molecular geometry. The electron group geometry will give you the geometric distribution of electron groups, which will be discussed in the example. Molecular geometry is the geometric arrangement of the atomic nuclei, which will be shown later. In most cases, central atoms have two or more electron groups distributed around them. The electron group geometries for these cases are for two electron groups, it will be a linear. For three electron group, it will be trigonal planar, and then for 4, tetrahedral, and 5, trigonal bipyramidal, and 6 will be octahedral. Please be reminded also when we talk about electrons in this module, we are talking about valence electrons. And then, in predicting VSPER model, the below table will be helpful. This is an expanded version of what I have read. In this, you will see the electron group geometry and the molecular geometry. So this is for 2. You have linear and you have a VSPER notation, which will also be explained in the example later. 3 and then 4, 5, and 6.
Before we proceed with our example, in applying VSPER theory, let's have a recap of our lesson, which is about atomic number, number of electrons, valence electron, and group number. Atomic number is equal to the number of electrons. And the number of electrons can be represented using electron configuration. And valence electron can be seen in the last orbital of the electron configuration, which also denotes the group number of an element. Group number of an element is group 1, hydrogen, going down. Group 2, beryllium, going down. Group 3, boron, going down. Group 4, carbon, going down. Group 5, nitrogen, going down. Group 6, oxygen, going down. Group 7, fluorine, going down. And helium for group 8, going down. Now, applying the VSPER theory, the first step is to do the Lewis dot structure. Let's take the example given, which is ICl4 negative. So, I has 7 electrons, which can be seen in your periodic table, plus chlorine also has 7 electrons. So, meron kang 4 na chlorine times 4, plus the negative sign indicates another electron, plus 1, which will be equal to 36 electrons. Okay? I will be your central atom since it is a single atom. I. Now you have 4 chlorine atom. So, Cl, 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 Cl. Forming bonds with Id. So, you have 36 electron. We'll count the bond as 2 electrons. So, 2, 4, 6, 8. 36 minus 8 will give you 28 electrons. Distributing the 28 electrons, 1, 2, 3, 4, 5, 6. 6 lang muna kasi dapat masatisfy niya yung 8 electrons na sinasabi ng octet rule. Then, let's distribute another 6. The chlorine. 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Now, 28 minus 24 will give you 4 electrons. These 4 electrons can be placed to the iodine, to the central atom. 1, 2, 3, 4. You now have your Lewis dot structure. Going back to, next step, step 2, count the number of electron groups around the central atom. So, electron groups, these are electron group. This is a bond group. And this is lone pair. So, counting it, so you have 1, 2, 3, 4 bond group, and you have 2 lone pair. Now, for number 3, referring to the electron group geometry, from the table given on page 4 and 5, you have 6 electron group. What is that 6 electron group? So, 1, 2, 3, 4, 5, 6. 6 electron group says that it is an octahedral. Step 4, referring to the VSPER notation in your table, you have AX4 E2. A is the central atom. X is the surrounding atom. And E is the lone pair of electron. In the VSPER notation table, you have a notation of AX4 E2 will give you a square planar. A is the I, Cl4 is the X, E is the lone pair in the Lewis dot structure. That gives you a VSPER notation or the VSPER theory to predict the geometric shape of a compound. Thank you.